Hey everyone, so let me discuss some examples on your first chapter, that is sequences. In that monotonic sequence. Okay, so this is the example. Check whether the sequence a1 is equal to 1 and an is equal to square root of 2 plus an minus 1. Here your n is strictly greater than 2 is monotonically increasing or decreasing. We have to check. So given data is what? A1 is equal to 1 and an is equal to square root of 2 plus n minus 1. So solution for this is, let a1 is equal to what? 1 and an is equal to what? Square root of 2 plus n minus 1, and here your n is greater than or equal to 2. So I am taking here in the place of n, replace the value 2. So a2 is equal to square root of 2 plus a of 2 minus 1, that is a1. Okay, so you know that a1 is 1. So therefore square root of 2 plus 1, so that is square root of 3. So means square root of 3 means the value of square root of 3 is strictly greater than 1. Therefore I am taking it as a1. So means your a2 value is greater than a1. Okay, your a2 value is greater than a1. So now suppose an is greater than an minus 1. Okay, so I am proving your sequence by I am using mathematical induction to prove your given example. Okay, so now I am taking an is greater than an minus 1 for n belongs to n. Here n is greater than 1. So here what I am writing here, I am adding to both sides. So then it will become 2 plus an is greater than 2 plus n minus 1. So later I am taking square root. Square root of 2 plus n is greater than square root of 2 plus n minus 1. Means this is n plus 1. So in the place of, if you replace in the example, that is a n plus 1, so then it will become square root of 2 plus n plus 1, n plus 1 minus 1 means an. So here I am getting this is an plus 1 and this is an. Okay, so by mathematical induction we can write n plus 1 is greater than n. Means here your all the value of the given sequence an is greater than previous one. So means here a2 is greater than a1, a3 is greater than a2, a4 is greater than a3. Okay, similarly an is greater than n minus 1. Next is that what is that? An plus 1 is also greater than an. So using mathematical induction we can say an is monotonically increasing sequence. Okay, so next discuss the convergence of the sequence an is equal to n plus 1 divided by n. Okay, for this solution, let an is equal to n plus 1. So if I divide this n by n, then it will become n divided by n plus 1 divided by n. N divided by n is what? 1. So n plus 1 is, replace the value n by n plus 1, then you get here n plus 1 is equal to 1 plus 1 divided by n plus 1. So therefore n plus 1 minus n is equal to 1 divided by n plus 1 minus 1 divided by n. So this is what? N minus 1 divided by n into n plus 1. This is minus 1 divided by n into n plus 1 is less than 0 for all n belongs to n. Okay, therefore n is monotonically decreasing sequence, because this is satisfying the condition of your monotonically decreasing sequence, that is n plus 1 is less than an. Okay, so because of that reason I am writing here the given sequence an is monotonically decreasing. So also I am taking here an is equal to 1 plus 1 divided by n. So if you put any value of n, so this is strictly greater than 1, means the given sequence is bounded. Okay, so therefore this is greater than 1 and this is less than 0, means the given sequence is bounded. So since an is monotonically decreasing and bounded below, therefore it converges to, it is convergent. Therefore limit n tends to infinity an is equal to limit n tends to infinity 1 plus 1 divided by n. This is equal to 1. So scratch it, this is not. So this is below and this is above, means the given sequence is bounded. Okay, so this is bounded. So therefore limit n tends to infinity an is equal to limit n tends to infinity 1 plus 1 divided by n is equal to, so if you replace the value of n by infinity, this is 1 plus 1 divided by infinity is 0. So the 1 plus 0 is 1. Therefore the given sequence an converges to what? 1. So okay, So next example is discuss the convergence of the sequence an where an is equal to 1 divided by n square plus 1 and n is equal to 1 plus 1 divided by 3 square 3 to the power n. So I am solving this example, first example, that is let n is equal to 1 divided by n square plus 1 and n plus 1 is equal to replace the value n by n plus 1, then you get n plus 1 divided by n plus 1 square plus 1. So this is equal to n plus 1 minus an, this is equal to, first write the value of an plus 1, later minus an value. Okay, so cross multiplication, you get n plus 1 into n square plus 1. So this is n into n square, so this will become n square plus 2n plus 1 plus 1, n square plus 2n plus 2. Okay, so this is n square plus 2n plus 2 into n square plus 1. So this is equal to, so n cube plus n plus n square plus 1. So multiply this, minus n cube minus 2n square minus 2n. So later you get minus n square minus n plus 1 divided by n square plus. So this value is less than 0. If you put n is equal to 1, so this is less than 0. Therefore, n plus 1 is less than an for all n belongs to n. So therefore, an is monotonically decreasing sequence. An is monotonically decreasing sequence. Also, an is equal to n divided by n square plus 1. So if you put any n belongs to n, it means if you put n is equal to 1, so this is strictly greater than 0 because n is equal to 1. So 1 square plus 1 means 0.5. 0.5 is greater than 0, means strictly greater than 0. Therefore, an is bounded below. Since an is monotonically decreasing and bounded below, it is convergent. It is convergent. Therefore, limit n tends to infinity, an is equal to n divided by n square plus 1. So if you take n square common, then n square into 1 divided by n into n square into 1 divided by n 1 upon n square. Put n is equal to infinity, this is also becomes 1 upon infinity 0. This is 1 plus 0. So 0 divided by 1 is 0. Therefore, an converges to what? 0. N converges to 0. So second example is that is let an is equal to 1 plus 1 divided by 3 to the power n. So put n in the place of n is equal to n plus 1, n plus 1 is equal to 1 plus 1 divided by 3, 1 divided by 3 square plus 1 divided by 3 to the power n plus 1 divided by 3 to the power n plus 1. So n plus 1 minus an. So left arm is what? 1 upon 3 to the power n plus 1, because all these terms vanishes with this. Okay, so this is strictly greater than 0, means n plus 1 is greater than an. So therefore, sequence an is monotonically increasing. Okay, also an is equal to 1 plus, using this is of the form gp. Okay, so then we use general form of that. Here a is equal to 1 and r is equal to 1 divided by 3. 1 into 1 minus 1 upon 3 to the power n plus 1 divided by 1 minus 1 divided by 3 is equal to, so this is 2 by 3. So after arrangement of terms, it will become 3 divided by 2 into 1 minus this. So 1 divided by 3 by 2 into this, it will become 1 divided by 2 into 3 to the power n plus 1, this 3 means 3 to the power n. This is the value of this is less than 3 by 2 for all n belongs to n. So therefore, an is bounded below. So since an is monotonically increasing and bounded above, therefore it is convergent. Limit n tends to infinity, an is equal to limit n tends to infinity 3 divided by 2 into 1 minus 1 divided by 3 to power n plus 1. So if you substitute infinity, this will become 1 upon infinity 0, 3 divided by 2. So means your sequence limit n tends to infinity n is equal to 3 by 2, means sequence n converges to 3 by 2. So if you have any doubts regarding these examples, you can ask. Thank you.